For today's lesson, we're going to take a deeper look into the convergence theorem of Fourier series. Now, just when I say that, we're going to use a lot of graphical representations to give us a better meaning of what we understand about Fourier analysis. What better way than to do 4 Fourier series or graphs of 4 Fourier series that I have over here. Now, I will particularly draw this lesson because it gives rise to a phenomena as well as application in physics, in particular electricity, or shall I say electronics. Right, so what I did over here is that I've considered 4 typical graphs of function f of x, and I have graphed out the certain Fourier series of it. Now, I must also say that there's a way to look at the Fourier series, and that is taking the n partial sums. Okay, since the board is a bit crowded right now, I'll just draw it right here. I hope you can see it. Now, when you write the Fourier series, you normally write from n equals to 1 to infinity, as in infinite amount of terms. But what does it mean by taking the n partial sums is that we will just consider from n equals to 1 to a certain value of n. Okay, so this value can be, I don't know, 5, 6. So basically, if there's a cosine and a sine terms, we're just going to take 5 of those and see what we get. Now, we expect that as n tends towards infinity, and given the certain convergence theorem rules that apply, this whole thing would converge to the function f of x. But the reason why we want to take the n partial sums is because we want to have a feel of what taking the summation is, and that's what we're going to do right now. So our first graph, or you can just take a minute to marvel at the graphs over here, and maybe I should just go right into it. Okay, the first graph is function f of x is equal to 2x from the domain of minus pi to pi. The Fourier series is given by this thing over here. So if you want to think about it graphically, when we take the n partial sum, so right now we're taking S4. Okay, S subscript 4, meaning the fourth partial sum. So basically we're going to have 4 sine terms. So if we take the fourth partial sum, the graph is going to be the dotted line. Okay. Now some points to notice that it's somewhat like a sine function. Now the reason is that it's very difficult to envision what the Fourier series is. You might be able to envision it if it's just a sine term, but notice that it's a sine term with the running variable changing the frequency of this thing over here, as well as the constant. So it's very difficult to envision. But what we can appreciate is that even though it's very difficult to envision, it somewhat follows a sine curve, or at least it follows a sine curve that converges to the function 2x, which is the graph over here. So you might suspect is that if, let's just say we take the 8 partial sum. So right now is we're taking the 4 partial sum, there's a lot of gaps over here. It does come true. If we take the 8 partial sum, the gaps become closer. So what we get is that the graph goes nearer and nearer to the function itself. So this one, is the 8 partial sum. Okay? So that's just to give you a feel about it. Going from the 4 partial sum to the 8 partial sum, and we go to infinity, it just converges to the graph. Now that's done. Okay. Now next is the modulus. Okay, modulus function f of x equals to modulus x is given by the graph over here, and the Fourier series is given by this thing over here, pi divided by 2, take away summation you have over there. So if I take the first partial sum, this is the graph that I get. Okay, again somewhat similar to the sign for the first function 2x and the Fourier series, but this time notice that we got a pi divided by 2. What does that mean? Well, this means that the Fourier series starts out with, it doesn't go to 0. It goes like this, but it does not go to 0. So there's basically a gap over here. But even though we are not able to see how that gaps get eliminated, we can immediately say that as we take more and more partial sums, the Fourier series will go closer and closer to the function over here, f of x. Okay, let's just say this is s equals to 9x. Now, I must again stress time and time again, the function is there is no clear derivative at x equals to 0. So basically you need to use the safe convergence theorems, but we should know by now that the Fourier series will converge to x equals to 0, or shall I say y equals to 0 and x equals to 0 when we take some infinity. Okay, 2 basic cases. Now, it's getting more interesting now, okay? Now, function f of x is equals to 1, negative 1 from minus pi to pi given by this thing over here. The Fourier series is given by this thing over here, and this is the graph that we get. Okay, now I would like to say that a few things. Again, as we take more and more partial sums, so this is s equals to 4, or the 4 partial sum. We take more and more partial sums, what we need to know is that this dotted line will verge closer towards this endpoints over here, right? As well as there's going to be more peaks. So there's going to be more peaks like that. Okay, why would there be more peaks? Well, basically we're taking more sine functions. Okay, so that is what we have. Now, before we talk more about this, let's just go quickly into the last one, which is function f of x is equal to 0, and for 0 to 2 is going to give by the cosine x function. The function graph is going to be like this. But the Fourier series is given by this thing over here, so by taking the fifth partial sum, this is what we get, okay? Now, let's magnify this area and see what interesting things that we get. So we magnify that area. This is the very interesting about this Fourier series. Fourier series of this function right here. Now, I'll label this as 1. If we take the fifth partial sum, you will notice that the Fourier series would be less than 1 at this point x equals to 0. So if we take the fifth partial sum like I've done over here, I'm magnifying this area, the Fourier series would go like this. Okay? That means it's going to be less than 1. I'm not too sure what the real value is, but it is less than 1. How about we would take now the 10th partial sum. The 10th partial sum, the Fourier series will give us something like this. Okay. Now, okay, this will be S10 and this will be S5. Okay, so if we take the 10th partial sum, the Fourier series at x equals to 0 is gonna be more than 1. Well, that's the case, I did test that out. Then later, when we take the 15th partial sum, the Fourier series would now go to 1 over here. Certainly by the convergence theorem, okay, and be very careful, the convergence theorem, what does the convergence theorem tell us? The Fourier series would tend towards, or converge towards half. Okay, 0 and 1 divided by 2 is half, okay? But what, it says that, as we take more and more partial sums, it is not very clear where the convergence, where the Fourier series converges to, because it starts with less than 1, it starts with 1, and then later it goes to 1, and later, maybe if we take the 20th partial sum, it would then, that's when it goes closer towards half. So as you can see now, convergence theorem is very important because looking at the Fourier series alone, okay, and taking the n partial sums, we do not know where the Fourier series ultimately converges to. We need to use the convergence theorem. But again, I say, the convergence theorem is coming from the function f of x. So, from here, we'll move back to our graph over here, this function over here, and this is the very interesting bit, okay? And now, I need to magnify this area over here, so which I would draw it much bigger, okay? So I hope that you guys can see. Okay, so as you know, this is x equals to 0, and let's just say this is 1, this is the y-axis. Okay. Now, what does the function tell us? The function tells us that the function is going to be like this, right? And what did I say just now? Well, we're concentrating on this function over here. Function x is equals to 1 from 0 to pi, and the Fourier series is given by this thing over here, okay? Now, as we take more and more partial sums, the peak is going to be closer to 1, right? So let's just say is at S5 would be like this, S10 is going to be like this, S15 is going to be like this, okay? But what I can say is that if you will notice, okay, and it's been tested out, the peaks may not necessarily go closer towards 1 over here. The peaks will get closer to 1, as we've done over here, or will get closer to x equals to 0, which is this line over here. However, intuition tells us, or at least the convergence theorem kind of suspects, or we kind of know that it would go towards 1 over here as we take more and more partial sums, okay? Sorry, not converge. If we converge to 0 over here. But if we take more and more partial sums, it seems that by intuition, these peaks will go towards 1 over there. Now, I know if we go to infinity, we will go back to 0, okay? Convergence theorem. But if we take more partial sums, it will go closer to 1. However, the phenomenon is that as we take more and more partial sums, these peaks will tend towards a limit. And that limit would not be 1. That limit instead would be 9% of the magnitude, okay, of the jump discontinuity. Okay, what does the jump discontinuity mean? Or magnitude of the jump discontinuity. The magnitude of the jump discontinuity is basically the distance from here to here. So, what I can say is that as we take more and more partial sums, the peaks would not go towards 1, it will go towards 9% of the magnitude of the jump discontinuity. And this is called Gibbs phenomenon. Okay, a very interesting phenomenon which I would like to study, discovered by Josiah Willard Gibbs by the turn of the century, not the 21st century, not the 21st century, the 20th century, okay, that he said that, it will approach a limit as we take more and more partial sums. Now, why is this important? It's important because if you will analyze certain circuits, right, if it's of high frequency, we are actually concentrating in this area over here. And basically, this Gibbs phenomenon tells us that this difference in the limit, right, will give us, extra stray capacitance, and that's not so good. And the other thing is that if we were to attenuate the lower frequencies, okay, as in we'll forget about the graphs by using a certain filter, you will know what I'm talking about, or if you electricians will know what I'm talking about, sorry, electrical engineers. Okay, this one over here, right, would you have a jump discontinuity, sorry, would have a jump discontinuity, and the limit would be obey Gibbs phenomena. So there'll be a difference in the magnitude. Okay, that may also be quite important. Okay, so basically that is for today's lesson. Introduction to Gibbs phenomena, what it means, and basically looking at the convergence of certain graphs.